Hey friends, it's Ben again. This is a video for Calc 3. I was reminded that I forgot to post something yesterday, and sorry about that, but I'm getting it out today. So the thing in question was that there was one problem at the very end of class, which boiled down to finding a rate of change, and just the phrasing wasn't enough. If you read the section and paid attention to their idea of the directional derivative, then you knew what it was talking about. But if you didn't read that, it was not nicely enough written to really be clear what it was I was asking. So I'm producing a quick video here that has just a little bit more background, which I couldn't get to in the 30 seconds we had left in class. So bear with me here, and we will look through a quick explanation of what's going on. All right. So I went ahead and wrote this out ahead of time because of the fact that I needed to draw a picture to help out. So the notion I'm trying to get across with the picture here is that you've got some sort of a function, f of xy. And of course, if you said z equal f of xy and you looked at a graph of this, the surface would look kind of like this. Okay. Oh, and these level surfaces that I've drawn here are just to kind of give us this sort of an idea on the plane of what's going on. So you could see that when we talk about a particular point here, this P, that would give us then some point on the surface. And when we talk about a vector that's in the plane, then when we look up onto the surface at that point, then by mapping that vector up, we would have kind of a slope figured out that would be a rate of change of a function. So in seeing what's happening with that, first of all, the notation is weird. It looks like it says duff. So it's a derivative in the direction of a certain vector u for your f, and then evaluated at a particular point p. So to see that, if you go ahead and think about it as a rate of change, then the easiest way to explain it is that at that point P, we're going to take a unit vector and multiply it by T, and that's going to be giving us like this point P and a line that's going through it with the magnitude of the derivative there of the R of T turning out to be 1. Okay, and that's just kind of the standard setup that we have on those. And so if we do that and then say something about f evaluated at R of T, and of course we're really interested in what's happening when T is equal to 0, but this f evaluated at R of T, the rate of change of it with respect to T, is just going to be given to us by the chain rule of taking the gradient of f and then dotting it with R prime of T. And so this directional derivative in the direction of u for your f evaluated at P, you'll plug in here and you'll end up with a gradient of f evaluated at P, and then you'll dot that with the derivative of your R vector of T will just be whatever the cosine comma sine is. But since this u vector is going to be something that gives you a direction, and it may not be given as a unit vector, then we just put the cosine theta sine theta in by taking the u vector and dividing it by its own magnitude. Okay, so super complicated sort of explanation for what's going on here to get this rate of change thing. But once you get this, it gives a perfect explanation of why the rate of change of f is largest in the direction of the gradient. The reason for that is that when you have a vector and you dot it with another vector and they're pointing different directions, then the value that you end up getting out of that is going to be less than the magnitude of either of those vectors, because you'll have that cosine, coming in there from dot products. But so if these two things happen to be pointing the same direction, the cosine of the angle between them will turn out to be 0, and you'll get then just the magnitude of this gradient, and then the magnitude of this unit vector, which is 1, times the cosine theta. I'm sorry, times the cosine theta, but the cosine theta is just 1 since the theta is really 0. Okay, so this provides kind of a nice insight for us, but then let's look at how you might be calculating something like this. So the example that I had written was find the rate of change of the r being x squared plus 2y squared, and it's at the point 1,5, and it's in the direction of -2, -3. So in doing that, you know that you're going to have to calculate the gradient anyway, and I don't know why I wrote a vector sign on that. Gradient of r, which will be a vector which is just 2x comma 4y, like that. And then the u vector that you want is just going to be the vector you're pointing at, the position you're pointing at, -2, -3, minus the position you're starting at. So it's just a vector going from 1, -5 to -2, -3. And that turns out to be what? -3, +2, okay? And you can clearly see that's not a unit vector, and we're going to need a unit vector when we do this, so we're going to divide it by its own magnitude. And so you've got the -3, 2, and we're going to divide by the square root of, let's see, 9 plus 4 is the square root of 13, okay? So this derivative in the direction of u of our r, that looks weird, our r is going to be equal to just the gradient of r dotted with this u vector over magnitude of u vector. So that is going to be 2x comma 4y, and we'll need to put in the point P here in a second, but then dotted with the -3, 2 divided by its square root of 13. And I'm going to have to put in here at P equals 1, -5. 1, -5. So that's 2 times 1 is 2, and -5 times 4 is -20, dot with -3, 2 over the square root of 13. And so you end up with a -6 minus 40 over the square root of 13, which is going to be then -46 over the square root of 13. Now I know what you're saying there. Ben, you wrote a 30. Nope, I totally didn't write a 30. You just imagined it. It was 13 all along. Okay. If you want to rationalize the denominator, you can, but I really don't see any reason to do that. So I would just leave it like that. But this is what you'll do if you're asked to get these directional derivatives, and they use that phrase about directional derivatives starting at a given point towards another point. You'll have to get the vector that takes you, from your start point to your end point. divide it by its own magnitude, and you take a dot product with this gradient. So not really anything too rough. To be honest, I feel like the only real big use of it is the establishment of that factoid there, that the direction of maximum increase is the gradient. So anyway, hope that's helpful. I'll talk to y'all later.